Okay, so I think I may have tricked you. Now, hopefully you were smart enough to think about this. But if it's at equilibrium, what's the definition of equilibrium to begin with? Well, the definition of the equilibrium is the forward rate has to be equal to the reverse rate. The rate going this way is equal to the rate going this way, just like dissolving and crystallization, just like vaporization and condensation. It's equal. Does that mean that the number of particles are the same? No, it does not. On both sides, it does not mean that. But equilibrium means that the rate of exchanges of opposing processes are equal. So in other words, the forward rate is equal to the reverse rate. Not greater than, not less than, it's equal to because it's at equilibrium. So because it's equal, then we can start doing this really cool thing where we can say that the rate of the forward reaction has to be equal to the rate of the reverse reaction. And this is where things get kind of interesting because now we can start thinking about relating the forward rate and the reverse rate. So here's what I'm going to do. I'm going to insert an equation here, like so. And what I will do is this. I know that the forward rate is equal to Kf times David. And so that's what I'm going to type in here. I'm going to say Kf, F times the concentration of David. And that I know then is equal to the Kr times the concentration of Dana. So then what they typically like to do in a situation like this is they like to take all the terms that are the same on the same side and make a fraction out of it. And so we've got K terms, or the rate constants. And so I'm going to do is I'm going to basically take the Kr and divide it to both sides. And I'm going to take the concentration of David and divide it to both sides. Therefore, I'm going to be left with something like this. Let me scroll down for you. What you'll be left with is something like this. So you're left with Kf over Kr, and that's got to be equal to the concentration of David, or excuse me, Dana, over the concentration of David. And if you can see, if you just cross multiply this, then it's going to be left with what we already know is true, which is the statement up above. So this is interesting because what we're saying is the forward rate constant is going to be bigger than the reverse rate constant because the concentration of Dana, we know, is bigger than the concentration of David. And so this is what we often refer to as the equilibrium constant. And let me show you what I mean. Instead of representing things like this, Kf over Kr for all chemical reactions or all equilibrium is often referred to as this thing called, I didn't mean to do a new equation. We'll see if this works. Keq. Keq means this. It is the equilibrium constant. So I'll write that out. Equilibrium constant. So this is huge because essentially what this equation right here reads is what stands for the equilibrium constant. So we can say, okay, not Kr over Ke, but instead we can say that the equilibrium constant is equal to the concentration of Dana particles over the concentration of David particles. So here's the big question now that we've written this equilibrium constant. What do you think the equilibrium constant would be for this reaction?